Welcome to our exploration of the mechanical properties of solids. In this chapter, we'll uncover the secrets behind how materials respond to forces, why some objects bend while others break, and what makes certain materials perfect for construction. Understanding these properties is crucial for engineers, architects, and anyone curious about the science behind everyday objects. Let's start our journey by defining some fundamental concepts and gradually build up to more complex ideas, ensuring a smooth and logical progression throughout. First, let's talk about stress. In physics, stress isn't about feeling anxious. It's the internal force per unit area that develops within a material when an external force is applied. Imagine stretching a rubber band. The force you apply creates stress inside the band. This concept is fundamental to understanding how materials react under different conditions, and it sets the stage for exploring related properties like strain and elasticity. Now let's define strain. Strain measures how much a material deforms in response to stress. It's the ratio of the change in length to the original length. If you pull on a metal rod and it stretches slightly, the amount it stretches compared to its original length is the strain. This concept helps us quantify deformation and is essential for comparing how different materials respond to the same force. Hooke's law is a cornerstone of material science. It states that within the elastic limit, the stress applied to a material is directly proportional to the resulting strain. In simple terms, if you double the force, the deformation doubles up to a certain point. This linear relationship is why springs and elastic bands behave predictably, and it's the basis for many engineering calculations. Every material has an elastic limit, the maximum stress it can withstand and still return to its original shape once the force is removed. If you stretch a spring too far, it won't snap back. That's because you've exceeded its elastic limit. Understanding this threshold is vital for designing safe and reliable structures, ensuring that materials don't undergo permanent deformation. Young's modulus is a measure of a material's stiffness. It's defined as the ratio of stress to strain within the elastic limit. A high Young's modulus means the material is very stiff and doesn't stretch much under force like steel. A low value means it's more flexible like rubber. This property helps engineers choose the right material for each application, balancing strength and flexibility. Relationship between stress and strain is fundamental in material science. Mathematically, stress equals Young's modulus times strain, as long as the material stays within its elastic limit. This equation allows us to predict how much a material will deform under a given load, making it an essential tool for engineers and designers. Bulk modulus measures a material's resistance to uniform compression. Imagine squeezing a rubber ball equally from all sides. The bulk modulus tells us how much it will compress. Materials with a high bulk modulus like steel resist compression, while those with a low value like foam compress easily. This property is especially important in applications involving fluids and gases. Shear modulus, also known as the modulus of rigidity, measures a material's resistance to shape changes when a force is applied parallel to its surface. Think of sliding the top of a deck of cards sideways while keeping the bottom still. That's shear. Materials with a high shear modulus resist this kind of deformation, which is crucial in construction and machinery. Poisson's ratio describes how a material changes in dimensions when stretched or compressed. If you pull on a rubber band, it gets thinner as it gets longer. The ratio of this lateral contraction to the longitudinal extension is Poisson's ratio. It's a key factor in understanding the three-dimensional behavior of materials under stress. Stress-strain curve is a graphical representation of how a material responds to increasing stress. It shows the elastic region, where the material returns to its original shape, and the plastic region, where permanent deformation occurs. By analyzing this curve, engineers can determine the strength, ductility, and toughness of materials, guiding their choices in design and safety. When a material is deformed within its elastic limit, it stores energy. This is called elastic potential energy. Think of a compressed spring or a stretched rubber band. When released, they return to their original shape, releasing the stored energy. This concept is vital in understanding how energy is transferred and conserved in mechanical systems. Plastic deformation occurs when a material is stressed beyond its elastic limit and undergoes permanent change. Unlike elastic deformation, the material doesn't return to its original shape. This property is important in processes like metal forming and shaping, where permanent changes are desired. However, in structural applications, plastic deformation can signal failure. Resilience is the ability of a material to absorb energy when deformed and release it upon unloading. A resilient material can withstand shocks and impacts without permanent damage. This property is crucial in applications like car bumpers, sports equipment, and safety gear, where energy absorption and recovery are vital for protection. Toughness is a measure of how much energy a material can absorb before breaking. It combines strength and ductility, making it a key factor in materials used for impact resistance. Tough materials can withstand sudden forces without fracturing, which is essential in construction, automotive, and aerospace industries. Compressive stress occurs when a material is subjected to forces that push it together. Imagine squeezing a sponge or pressing down on a column. Materials must be able to withstand compressive stress to support loads without buckling or collapsing, making this property critical in building foundations and pillars. Tensile stress is the opposite of compressive stress. It occurs when forces pull a material apart, like stretching a rope or a steel cable. Materials with high tensile strength are essential in bridges, cables, and any application where pulling forces are common. This property ensures structures remain intact under tension. Shear stress arises when forces act parallel to a material's surface, causing layers to slide past each other. This is common in bolts, beams, and machine parts. Materials must resist shear stress to prevent failure in joints and connections, making it an important consideration in mechanical and civil engineering. Elasticity plays a vital role in engineering applications. From designing bridges that flex under heavy loads to creating shock absorbers in vehicles, understanding elasticity ensures structures can handle stress without permanent damage. Engineers use elastic properties to optimize safety, durability, and performance in countless products and systems. Steel is the material of choice in construction due to its high strength, ductility, and resilience. It can withstand both tensile and compressive stresses, making it ideal for skyscrapers, bridges, and other large structures. Its predictable behavior under load and resistance to fatigue make it a reliable and safe option for engineers. Elastic fatigue occurs when a material is repeatedly stressed and gradually loses its ability to return to its original shape. Over time, even small repeated forces can cause permanent deformation or failure. This phenomenon is important in designing parts that experience cycles of loading, such as springs, bridges, and machinery. Elasticity isn't just for engineers, it explains many everyday phenomena. From bouncing balls to the stretch in your clothes, elastic properties are all around us. Understanding how materials stretch, compress, and recover helps us appreciate the science behind common objects and informs better choices in product design and use. Let's recap the three main types of stress: tensile, compressive, and shear. Each type affects materials differently and requires specific properties for resistance. Engineers must consider all three when designing structures to ensure safety and functionality under various loads. Materials can behave elastically or plastically depending on the amount of stress applied. Elastic behavior means the material returns to its original shape, while plastic behavior results in permanent deformation. Knowing the difference helps engineers predict failure points and design safer products. Ductility is a material's ability to be stretched into a wire, while malleability is its ability to be hammered into thin sheets. Both properties are important in manufacturing and construction, allowing materials to be shaped without breaking. Metals like gold and copper are known for their high ductility and malleability. Brittleness is the tendency of a material to break without significant deformation. Glass and ceramics are classic examples. While they may be strong, they lack the ability to absorb energy and deform, making them unsuitable for applications where impact resistance is needed. Hardness measures a material's resistance to scratching or indentation. Diamonds are the hardest known material, while softer materials like lead can be easily scratched. Hardness is important in selecting materials for cutting tools, wear-resistant surfaces, and protective coatings. Several factors influence the mechanical properties of solids, including temperature, impurities, and the material's internal structure. For example, heating can make metals more ductile, while impurities can strengthen or weaken a material. Understanding these factors helps engineers tailor materials for specific uses. Mechanical properties are tested using various methods, such as tensile tests, compression tests, and hardness tests. These experiments provide data on how materials behave under different loads, guiding engineers in material selection and quality control. Mechanical properties are crucial in construction. From choosing the right steel for beams to selecting concrete mixes for foundations, understanding how materials respond to stress ensures buildings are safe and durable. Engineers rely on these properties to design structures that withstand earthquakes, wind, and heavy loads. In machinery, mechanical properties determine the performance and lifespan of parts. Gears, shafts, and springs must resist wear, fatigue, and deformation. Selecting materials with the right combination of strength, toughness, and elasticity keeps machines running smoothly and safely. Mechanical properties are vital in transportation, from cars and trains to airplanes. Materials must be strong yet lightweight, resistant to fatigue, and able to absorb impacts. Advances in material science have led to safer, more efficient vehicles that can handle the demands of modern travel. Mechanical properties aren't just for big projects, they're part of everyday life. The flexibility of a plastic bottle, the strength of a metal spoon, and the resilience of a running shoe sole all depend on these properties. Recognizing them helps us understand why products are designed the way they are. Choosing the right material for a job involves balancing mechanical properties with cost, availability, and environmental impact. Engineers must consider all these factors to ensure the final product is safe, efficient, and sustainable. Material science is constantly evolving, with new materials like composites and alloys offering improved mechanical properties. These innovations enable the creation of lighter, stronger, and more durable products, pushing the boundaries of what's possible in engineering and technology. Modern engineering must also consider the environmental impact of materials. Recyclability, energy use in production, and long-term durability all play a role in material selection. Sustainable choices help reduce waste and conserve resources for future generations. Safety is paramount in engineering. Standards and regulations ensure that materials meet minimum requirements for strength, toughness, and other properties. Adhering to these standards protects people and property, making them a cornerstone of responsible engineering. The future of materials science is exciting, with research focused on smart materials that adapt to their environment, self-healing materials, and more. These advancements promise to revolutionize industries, making products safer, more efficient, and longer-lasting. Let's summarize the key concepts covered: stress, strain, elastic and plastic behavior, modulus values, and the importance of mechanical properties in engineering. These ideas form the foundation for understanding how materials behave and how we can use them to build a safer, more efficient world. For students, mastering these concepts means practicing problems, visualizing stress-strain curves, and connecting theory to real-world examples. Focus on understanding definitions, relationships, and applications to build a strong foundation in material science. It's easy to confuse terms like stress and strain or elastic and plastic deformation. Remember, stress is the force per area while strain is the resulting deformation. Elastic changes are reversible, but plastic changes are permanent. Clarifying these distinctions helps avoid mistakes in both study and practice. Mechanical properties of solids connect to physics, chemistry, and engineering. Understanding these links deepens your appreciation for how science and technology work together to solve real-world problems, from building bridges to designing smartphones. To reinforce your understanding, review key questions. What is stress? How does Hooke's law apply? Why is steel used in construction? These questions help you test your knowledge and identify areas for further study. The mechanical properties of solids have a profound impact on our daily lives, from the safety of our homes to the reliability of our vehicles. By understanding these properties, we can make better choices as consumers, engineers, and citizens. Congratulations on completing this journey through the mechanical properties of solids. With this knowledge, you're better equipped to understand the world around you and tackle more advanced topics in materials science and engineering. Stay curious, keep exploring, and apply these concepts wherever you go.